Have you ever wondered what space travel might be like in the future? In many science fiction stories, in the future, humanity has spread out across the solar system, colonizing planets and asteroids. Given the hundreds of millions of kilometers between us and even the closest orbital bodies, this is not easy to do in real life, at least not with our current level of technology. NASA predicts that it will take 7 months to make it to even our closest neighbor, Mars. This is why sci-fi writers often invent powerful engines on their spacecrafts, warp drives, Epstein drives, and hyperdrives that allow humans to cross those distances in days or minutes rather than months or years. These conventional flight times occur because of the limitations in conventional rocketry. But new technology is arising, something that feels like it's straight out of sci-fi, that might one day completely replace conventional rockets. With its greater efficiency, those month-long flight times could become mere days. And while the technology is still under development, there are examples of it being used in outer space missions right now. What is this technology? Ion engines. And with them, the future might be a lot closer than you think. I'm Alex McColgan and you're watching Astrum. Join with me as we learn more about this developing technology and learn more about these devices that may well be the future of space travel. To begin with, for those who are unfamiliar, what is an ion engine and how are they different from conventional rockets we know today? All rocketry works under the principle of conservation of momentum. If you want to go up, you must send something else flying down with enough momentum to equal the upward momentum you wish to achieve. Conventional chemical rockets do this by burning rocket fuel. Oxidizer mixes with a chemical like liquid methane, heating it and causing it to expand. By sending out this stream of highly energized exhaust from the bottom of the rocket, the top is sent flying upwards, kind of like releasing the air from inside a balloon to send it whizzing around the room. Momentum is conserved in these cases. In our example with the balloon, the momentum of the air leaving the balloon equals the momentum of the balloon flying around. With the rocket, the momentum of the exhaust equals the force of the rocket going upwards. In theory, you could travel around in space simply by having a very large balloon and releasing its air. However, you would run into a problem with this method. You would run out of air very quickly and then would not be able to produce any more thrust. Balloons are not very efficient forms of rocket propulsion. To a degree, this is also the problem with our current chemical rockets. Although burning the fuel does give it more kinetic energy than simply squeezing it out of a balloon, chemical rockets are still not that efficient, as there is an upper limit to how fast you can accelerate exhaust material by burning fuel. Rather than burning it hotter, if you want to go faster with such a rocket, the only solution is to burn more fuel, which means you need to carry more fuel, which means your rocket has to be bigger and heavier, requiring even more fuel. And once you run out of said fuel, that is it. You can produce no more thrust. Conserving their fuel is the reason the NASA trip to Mars will take 7 months. There's no way they could have a large enough rocket that could carry enough fuel to accelerate passengers all the way to Mars. Consider the over 60-meter size of some of the rockets being launched currently, such as the Artemis 1 SLS rocket that got a spacecraft to the moon recently, a much closer target. Its main core stage was filled to the brim with 2.8 million liters of fuel. That fuel was all burned up in just the first 10 minutes after launch. To carry enough fuel to accelerate all the way to Mars would need a ridiculously large ship, which would need a monstrous amount of thrust simply to get it off the ground. It's just not efficient. Momentum is equal to mass times velocity. Chemical rockets try to go faster by simply throwing more mass out the back of their thrusters. But what if instead we increased the velocity at which that mass was thrown? That would also increase momentum, giving you more thrust. And this is where ion engines come in. Ion engines attempt to give thrust electrically to their propellant. Rather than burning fuel to cause rapid expansion, they attempt to create ions, or charged particles, that then are accelerated along electromagnetic fields, sometimes to speeds of 146,000 kilometers per hour, depending on the model. The more electricity you have, the more momentum you could impart to such a particle. And the faster it leaves the back of your rocket, the more momentum that your rocket gains to move forward. This means that you could get away with using far less fuel on your trip, provided that you could create enough electrical energy to accelerate your particles. The takeaway is that ion engines are much more efficient than chemical rockets. Chemical rocket fuel efficiency could achieve up to 35% efficiency, while ion engines could manage 90%. Different models vary in their efficiency, but all require far less propellant to achieve acceleration. So much so that they can literally accelerate for years. And this acceleration adds up. NASA space shuttles have top speeds of 29,000 kilometers per hour. Ion thrusters can achieve speeds that are 11 times that. The upper cap is how much electricity you can produce, not how much fuel is in the tank. So, if ion engines are so superior, why haven't we already started using them? That question is a little misleading. We have been using them. The recent NASA DART mission was equipped with a next gridded ion thruster, ready to be used in the event that its conventional thrusters failed. Deep Space One visited distant comets while using an N-star ion engine. For a period between 1972 and the late 90s, Soviet satellites made use of Hall effect thrusters, a type of ion propulsion, as stabilizers on their satellites. This functionality is still being used on satellites today. SpaceX's Starlink satellites also use Hall effect thrusters. Even entire space stations have been propelled by these thrusters. The Chinese Tiangong space station is moved by propellant, but also 4 Hall effect thrusters, which are used to adjust and maintain the station's orbit. These thrusters have reportedly been firing continuously for 8,240 hours with no problems. But as you might have intuited, there is also a problem with current generation ion thrusters, which means they're not yet ready to replace all conventional rockets. They have a fatal flaw, an Achilles heel. Ion thrusters on the market today have terrible oomph. To illustrate this point, if you were to take an ion thruster and were to hold out your hand to try to stop it moving, the force you would feel would be roughly comparable to the weight of a single piece of paper. That is the trade-off. Ion thrusters can accelerate for years. They usually use chemically inert gases as their fuel source, so are very safe. They can accelerate particles up to huge speeds, but the number of particles being accelerated is small, so the force of this thrust is tiny. An ion engine cannot produce the large enough thrust needed to get a spacecraft out of Earth's powerful gravity well by itself. Of course, in space, with no air resistance to fight against and with enough time, this tiny thruster can add up. Even a gentle acceleration can get you where you want to go if nothing opposes it. For point of reference, some ion engines in space can take a couple of days to accelerate a spacecraft up to about the speed of a moving car. This means that ion thrusters have a niche on long-distance missions, ones that can get away with only gentle force to maintain orbits, or for moving very small things like tiny satellites. But they are a long way away from being able to carry humanity a long way away. There are other problems to overcome. Ion engines work by creating circuits, moving patterns of electrons that can carry charge and create electrical and magnetic fields. However, ions from the atmosphere can interfere with the delicate balance of these circuits. If the circuit breaks down because extra negative charges are coming in when they shouldn't, or are bleeding out unexpectedly, the engine loses its ability to create the right fields, which means it can't accelerate reliably. Not only that, but the best fuel sources for ion engines, the chemically inert xenon, is very rare and expensive, $1,000 per kilogram. Ion engines will need to overcome all these problems if they are to become the primary form of space transportation in the future. That said, there are some efforts being made to do just that. Helicon thrusters are a new type of ion thruster that are being developed by the European Space Agency in collaboration with the Australian National University. they are making breakthroughs that improve thruster efficiency even further, decreasing the wear on parts, and making it so ion thrusters are even better suited to those long space voyages. In terms of fuel source, some ion thrusters under development are being built in ways that allow them to use a much wider range of fuel sources. The complexly named magnetoplasma dynamic thruster has configurations that allow it to use hydrogen, argon, ammonia, or nitrogen as propellant. In certain settings, it can even use the ambient gas in low Earth orbit. Imagine having a spaceship whose fuel source was literally air, whose only waste exhaust was that same air. This is a trait shared by the ever-improving variable-specific impulse magnetoplasma rocket, which is particularly intriguing as it can use almost anything as a fuel source, although it has a preference for argon. Argon is 200 times cheaper than its competitor, xenon, making it a much more viable fuel source. Vasimer also has more oomph than other ion thrusters. The designers of Vasimer claim that it could take astronauts to Mars in just 39 days. However, the technology has some kinks to work out. It is extremely power hungry. It is designed to heat plasma inside it to 1 million degrees Celsius, or 173 times the temperature of the Sun's surface. We do not yet have power sources efficient enough to feed this engine at the levels necessary for that 39-day trip, and even when we do, unsurprisingly, getting rid of all the excess heat this creates is problematic, as in space there is nothing to transfer the excess heat to. These up-and-coming lines of ion thrusters all still have a long way to go before they will be able to totally replace conventional rockets. While their efficiency is incredible, their poor thrust leaves much to be desired. But even if an ion engine is never developed with the thrust necessary to get out of a planet's gravity well, this capability to significantly reduce travel time to distant planets, and its advantages as a way of efficiently moving satellites, means that ion thrusters already have their niche. Scientists keep searching for solutions to ion thrusters' technological challenges. For now, conventional chemical rockets remain the only option for short-burn, high-thrust journeys. But one day, if those challenges are overcome, this may no longer be true. Ion engines might become the only type of engine worth using. Then, the solar system as a whole will open up to us like never before. It might one day be possible to pop over to Mars for a holiday. Perhaps this is one more example of where science fiction one day becomes science fact. It doesn't take much to learn that the Earth is facing an energy crisis. Fossil fuels are finite, but also represent 80% of the source of our electricity. At some point, we will inevitably run out, whereupon we will either need to get our energy from somewhere else or brace ourselves for the shocking reality of a world without machinery, computers, and phones. If the idea of pushing a plow all day in an agrarian society doesn't quite align with your life goals, then you'll be in favor of the alternative, finding a different energy source for most of society's energy needs once all the oil, coal, and gas runs out. You've likely heard of options like wind, geothermal, or tidal power. But do these approaches dream big enough? Could the answer to the energy crisis actually be something that sci-fi writers have been talking about for over 60 years? Although it's a long way off, could humanity actually build a Dyson sphere one day? And just how far off are we from being able to do this? I'm Alex McColgan, and you're watching Astrum. Join me today as we examine the case for Dyson spheres and discover how the maths behind these gargantuan structures might make them not just possible, but actually plausible for our future energy supply. I was recently going through an online course when I came across the topic of Dyson spheres, and they really caught my imagination. Dyson spheres are crazy. They were first explored in a paper by British-American theoretical physicist and mathematician Freeman Dyson, who was considering the way hypothetical alien civilizations might try to power their society and how we might spot them. All life requires energy to live, and the more advanced a society, the more energy it seems to end up needing. Dyson thought that if an alien race was spacefaring, they might build a habitat in space near their local star to take advantage of its solar radiation. Over time, more and more habitats would be built, until one day, most or all of the star would end up surrounded by a truly mammoth shell of habitats, which would capture and utilize all the radiation the star was emitting. This shell was eventually considered one single structure and came to be known as a Dyson sphere. Creating one would give a species access to a ridiculous amount of energy, sending their civilization into the next stage up in galactic exploration and expansion. Dyson got the idea after reading a science fiction book known as Star Maker, something he publicly credited, and indeed, this idea does sound a little like something out of sci-fi. It would be very hard, and potentially take a very long time to build anything so large, and seems to be well beyond the capabilities of our own current civilization. That said, this sci-fi idea might need to be something we consider a little more closely. As the course I was learning from pointed out, there are just over 8 billion humans on Earth right now, and we collectively use 4 times 10 to the power 20 joules, or 400 quintillion joules of energy per year. This sounds like a lot, and it is, particularly when you consider that the current estimated amount of remaining energy available in oil reserves is 6 times 10 to the power 22 joules, or 60 sextillion joules. Doing a little division, it becomes clear that we only have 150 years of oil reserves left if we continue burning it at our current pace. 150 years is really not that many. And given how quickly we are ramping up energy consumption globally, it's fair to assume that we might run out of oil sooner, even if more oil reserves can be found. Which is why finding another mass source of energy, such as utilizing the energy available in sunlight, actually is quite appealing. Compared to what we gain from fossil fuels, the sun produces a staggering amount of energy, even if you're only considering the amount of light that hits our planet's surface directly. Let's use a little equation to show you what I mean. At this distance, the energy we receive from the sun is around 1,360 joules per squared meter per second. Multiply this across approximately 1.1 times 10 to the power 14 square meters of the sun's circular area as it cuts through space. Then multiply this again across the course of a whole year, all 31,536,000 seconds of it, and we would receive around 4.7 times 10 to the power 24 joules of energy. That's 10,000 times the energy we are currently using from oil, more than enough to cover our needs, assuming we could harness it. Obviously, capturing all that sunlight is a bit tricky to do in practice. And obviously, if we were to capture all of it, that would make life a bit difficult for any plants on the planet wanting to use that light for photosynthesizing purposes. But even if we got to the point where we were only using half of all that available energy, we would completely remove our need for fossil fuels and could have the energy necessary to support a significantly larger population at the same time. Forget 8 billion, we could sustain 40 trillion people here on Earth, at which point the biggest problem wouldn't be how to give all those people the energy you'd need to sustain their lifestyles, but where to put them all. Increasing the population density by 5,000 times would go from there being on average 7 people per square kilometer to being 35,000 people per square kilometer, or 1 person per 3 square centimeter. So making this work might be a bit of a challenge without some creative housing plans. Regardless, this does seem like a good solution to the energy crisis. The joules are there. So if we can already cover our population's needs by fully accessing only a small fraction of the sun's total output, the part hitting the Earth, we probably don't need to harness any more of it just yet. However, looking to the future, that won't always be the case. Reaching 40 trillion people
is actually not that far off, at least on the scale of human history. Our population is currently growing at a rate of 0.88% a year. At times this number has been as high as 2%. For simplicity, let's just take a nice round 1% figure and calculate using that. If we increase for the population size by 1% every year, the cumulative growth of the population would hit 8.8 billion in a decade, 22 billion in a century, and 40 trillion in only 800 to 900 years. So what might be the solution when that happens? Why, doing as Dyson's hypothesized alien races do, and increasing the amount of solar energy that we capture, probably by building solar panels or mirrors and sending them into orbit around the sun. As the course I was learning from highlighted, with more solar collection tools comes more benefits. A Dyson sphere, or a Dyson swarm, as this segmented configuration is technically known as, offers power that's many orders of magnitude higher than what we can do with just a planet's worth of surface area. Harnessing it would elevate us to a higher level of civilization, one that went from controlling its planet to harnessing its entire solar system, perhaps giving us the springboard that could truly kickstart our expansion across the stars. On the Kardashev scale, a method of measuring a civilization's advancement by evaluating how much energy they could potentially use, this would tip us from a Type 1 civilization into a Type 2. In case you're wondering, we're currently only about a Type 0.7, as we've not quite managed to make use of all the energy on the planet, while a Type 2 would have access to all the energy in the solar system. To get to a Type 3, we'd have to harness the entire galaxy, so that's a long way off. Still, the energy levels a Dyson sphere could produce are already so extravagant, it seems silly to our current understanding to even contemplate them. If we completed a Dyson sphere, or a Dyson swarm, we would go from 4.7 septillion joules to 10 decillion joules, increasing our energy levels by 20 trillion times. That should be enough to keep the lights on for the foreseeable future. Technologically speaking, we are pretty much at the point where we could make a solar panel that could capture sunlight from the sun and send it towards Earth, or even easier, we could simply create space mirrors to reflect the light towards where we needed it, say an orbiting space foundry outside of Earth's atmosphere, with the same end result. This might be the simpler idea, as then you don't have to worry about how to transfer all the generated electricity from the solar panel back to Earth. You can just send the sunlight directly to wherever it's needed, although you would be sacrificing some habitability on the Dyson sphere itself. Placing mirrors into stable orbits is not impossible for us, and having them be able to maneuver slightly to reorient through the year doesn't sound too implausible. So then it's just a question of how much materials would this require. Unsurprisingly, depending on what distance you created your shell, a Dyson sphere would need a lot of material. For instance, the course I was learning from identified that building a Dyson sphere that coincided with the Earth's orbit would need about 6% of the entire volume of the planet, even if the panels were less than a millimeter thick. This is hardly ideal, even if we could selectively drill out the materials that were needed. But if we instead built a sphere at a much more compact distance from the Sun, say at the distance of Mercury's orbit, then the material requirements become much more feasible. Mercury itself contains all the raw material that might be needed for such a structure. And as far as we know, there is no one living on Mercury who would complain if we were to fill it with holes. But then, the last issue to consider, other than the moral question of whether it's okay to tear apart an entire planet purely for our own benefit, is that it's obviously an energy-intensive process. Materials have to be mined, processed, then made into their components. The solar panels or mirrors would need to be built, and even once that's done, they need to be lifted out of Mercury's gravity well. And that's a particularly energy-intensive process. If we utilized all the sun's energy that was hitting the planet Earth and spent it all on doing nothing but lifting mirrors for our Dyson sphere out of Mercury's orbit, we can calculate how long it would take us to lift enough mirrors to complete the entire shell. We know the formula for overcoming the gravitational binding energy of Mercury, which for Mercury gives us roughly 2 × 10 to the power 30 joules. We already know how much energy we at maximum could get from sunlight here on Earth, 4.7 × 10 to the 24 joules. So then it's just a simple matter of dividing the first by the second. And voila! This process would only take a measly 425,000 years, during which time there would be no energy left to support Earth's population or give light to our plants, because we're using it all to build a Dyson sphere. Maybe this isn't such a viable idea after all. But wait, there's one last point to factor into this. That's the fact that once our mirrors came online, they could start providing energy of their own to help pay the energy costs. This would then become an exponential process, with no additional input required from Earth, perhaps except for a little oversight. One mirror would provide energy to make a second, then both would double to make 4. Every instance you would be doubling your number of mirrors, and once you get exponential growth involved, depending on how much energy you put into the system at the start, the entire thing could be completed much sooner. According to some calculations, Mercury would be completely disassembled in as little as 31 years. In other words, if we started building one right now, you might live to see its completion. Ethical considerations aside, such numbers really bring into focus the viability of this project. Something that takes half a lifetime to complete is certainly ambitious, and the initial cost might indeed be great. There would be some practical considerations to think about in terms of the best way to set up mining operations on Mercury, but these are questions we're already putting our minds to anyway. Scientists are currently working out how to set up bases on the moon with similar intentions. We're not far away from doing the same on other planets once we have the techniques down. In other words, there really aren't very many barriers left towards attaining the immense energy of the sun. A Dyson sphere might well be another example of something that sounded like science fiction to us, but will turn out to be something our children or grandchildren will one day come to take for granted.
What is a human? We come in all shapes and sizes, colors and genders, and yet we find it still fairly simple to identify in our heads, yes, that's a human, or no, that's not. But this might not always be quite so easy to do. While humans have remained fairly consistent over the last 10,000 years, there are advances in the works that might make things a little murkier. We are on the cusp of a technical revolution that might redefine what makes us, us. That technology is gene editing, and it is not science fiction. NASA is already looking into using it on astronauts, and for good reason. It is likely an unavoidable necessity if we want to settle on other planets. Why is that? And what are the long-term implications if we let this genie out of its bottle? And perhaps, most importantly, what will it mean to be human 1,000 years from now? I'm Alex McColgan and you're watching Astrum, and in today's video we will attempt to find out. There is a pernicious obstacle out there for any would-be spacefarer. It is one you've likely heard of, but perhaps you've not realized how serious it was. Beyond the protective shroud of our planet's magnetosphere, radiation is a big deal. Even on Earth, we cannot avoid radiation. We are subjected to small doses of it every year, just from the rocks that make up the planet and the tiny amount of cosmic radiation that seeps into our atmosphere. There is no truly safe amount of it, but the tiny dose of roughly 3 millisieverts a year is usually no bother to us. A single millisievert is the equivalent of about 3 chest x-rays, so as these are spread out over the year, it gives our body time to recover from any damage such radiation causes. But once you start leaving the Earth's magnetosphere, the radiation dosage goes up. merely standing on the moon increases your dosage 200 times. Solar particles ejected from the sun and background cosmic radiation slice through any unprotected astronaut's body up there, causing damage to their DNA that can lead to short-term acute symptoms like fever, nausea, and vomiting, and also long-term health problems like cancer and sterility. This is problematic enough that most space agencies put a lifelong cap on how much radiation an astronaut can receive before they're permanently grounded, around 1000 millisieverts. Once you've been exposed to that much radiation, you're not allowed into space again. But problematically, even with all the shielding that humans can muster, it is currently estimated that the round trip to and from Mars will give you a dosage as high as 1200 millisieverts. In other words, a completely fresh astronaut will be able to make one trip to Mars and their career will be permanently over. And that's just Mars. If ever humans want to colonize other places in the solar system, such as the icy moon Europa, they would face 5,500 millisieverts in just a single day. At that level, their odds of dying in the next 30 days is 50%. Yet, it will be necessary to leave Earth. While it may seem a long way away, 6 billion years from now, our sun will become a red giant. At that point, it will expand and engulf the inner planets of the solar system. Every species on the planet at that time, every work that we humans have created, will be gone forever, consumed in a raging inferno, unless we've spread out to where our sun gone berserk can't reach us. And that's not even to mention the fact that a planet-ending asteroid could hit us with a dinosaur-level extinction event long before that. We're actually overdue the next one, statistically speaking. So going to space seems advisable. If we have colonies on more than one planet, it reduces the risk of an asteroid taking us all out, the cosmic equivalent of not putting all our eggs in one basket. This is why, on the 13th of August 2021, NASA announced that it had completed a successful test of genome editing aboard the International Space Station. It should be noted, there are different levels of gene editing. The test done by NASA was to break the DNA of yeast, remove a section, and then replace it with a sequence of healthy yeast DNA through a technique known as CRISPR. As radiation causes damage to DNA, being able to remove segments and replace them with healthy segments is a convenient genetic maintenance, the equivalent of replacing a puncture on a tire. This already would be useful to astronauts traveling through space, as it would allow them to repair ongoing damage to their DNA by constantly replacing damaged parts of it. But genetic editing and CRISPR can go one step further. There is nothing to say that the replacement DNA has to be the same as the original. CRISPR has been used successfully to implant totally new genes into test subjects, giving them desirable traits according to the gene editor's aims. For instance, genetic diseases like sickle cell anemia result in low levels of hemoglobin in the blood. CRISPR allows these harmful genes to be removed from a cell and replaced with a healthier version that does produce the needed hemoglobin. Trials are already underway to encouraging success. But it doesn't stop there. CRISPR can borrow genes from entirely different species. Tardigrades are microscopic little animals that carry the nickname water bears. Their claim to fame is that they are resilient to all sorts of harsh environments. They can survive radiation, desiccation, which is being completely dehydrated, and have even survived the harshness of space. That radiation resistance is particularly interesting to us, and the result of a protein they produce called DSUP. In 2015, geneticists successfully edited the gene that produced DSUP from a tardigrade cell into a culture of human cells. Incredibly, the human cells became 40% more resistant to radiation. This technology is here, and is already quite accurate and versatile. Of course, there is still a lot to learn about the human genome. It turns out that the one gene, one trait model is too simplistic. One gene can do several things, and editing one can have unexpected knock-on effects throughout the body. As such, any introduction of tardigrade cells into humans must be done slowly and cautiously. But it does seem likely that over time, scientists will understand what each gene does and how to balance the pros and cons of gene editing. Which raises an ethical dilemma. Just because we learn how to, and it's entirely possible that we as a species will master how to do this, should we? That's not really for me to answer, but I will point out that this is already going on. Aside from the ability genetic modification is giving us to cure genetic diseases or to repair damaged DNA, which I imagine most people would be fairly okay with, even genetically modified designer babies have been carried to full term. A Chinese doctor in 2018 announced to the world the birth of 2 gene-edited babies, Lulu and Nana. The 2 children had been engineered before birth to be resistant to the strain of HIV. The only problem was the doctor had not told anyone that was what he had been doing. His work was shut down within days by the Chinese government, and in 2019 he was jailed. But to some respect, the genie is out of the bottle, and we have to start asking how we would like to see this technology applied. It may become necessary for anyone traveling to Mars or to the other planets in the solar system to receive gene therapy, conferring on them this resistance to radiation. And as the techniques for conferring genes from other species improves, specialized hybrid humans might become more and more common, or even required in some areas. While replacing the genes of every cell in our bodies is still a ways away, there is a possibility that it will one day happen. And if it does happen, what would that mean for us? Well, want to settle on a warm or cold planet like Mercury or Pluto? Certain traits might be conferred from extremophiles that give you resistance to extreme temperatures. There are many species of bacteria out there that survive perfectly well in icy conditions. It might be useful for any human settling out there to do the same. Speaking of Pluto, low light environments might make it advantageous to either gain improved low light vision, larger eyes, or to gain traits like echolocation, like dolphins or bats. 1,000 years into the future, this will very likely be possible. How about breathing underwater? We could take the DNA of aquatic creatures and give humans gills. That might help overcrowding on Earth too, by allowing us to inhabit oceans, as well as allowing us to settle on any aquatic worlds we might one day find. Want to travel on long voyages through space? Even with faster rockets, traveling to other stars might take hundreds of years. It might be useful to be able to hibernate in such a condition, or to have more efficient energy intake systems, meaning you need less food. One day, humans might introduce chloroplasts into their skin, supplementing energy intake with photosynthesis, like plants do. Electricians might gain the ability to sense electric fields, like hammerhead sharks. Our senses might expand into other spectra of light, allowing us to see X-rays or infrared. Seeing heat might be incredibly useful in some lines of work. Seeing radiation might be handy if you're considering stepping outside into a solar storm. Our ability to eat a varied diet might increase. There are worms today that can eat plastic. Maybe we one day will be able to do the same. Increased longevity, enhanced intelligence. The possibilities are endless, as extensive as the genetic catalogue of any species that has ever existed and ever will exist, and even further. One day, we may get so proficient with genetic editing that scientists will write their own genes from scratch, granting traits as desired. Christopher Mason, a geneticist and computational biologist who has worked with NASA on 7 projects, believes in his book, The Next 500 Years, that humans might one day customize their traits on the fly. Given the methods described above, people could find themselves in a state where they decide, I want to turn these genes on for tonight, or I want these genes active for summer. This is not necessarily a bad thing. Humans already adapt in many different ways, but it does raise serious philosophical questions about what it means to be human. Our DNA would no longer define who we are, as it would be under our control. While initially the technology would only be available to the rich, 1,000 years from now, it could be so common and so well understood that it could be available to everyone. Children could be given homework assignments on changing genes at school, according to some theorists. What is a human? Is it our DNA? Our ability to communicate? Is it what we look like? 1,000 years from now, humans might look more different from each other than ever. Will it bring a deeper segregation to our society than what we already have? What would the ethical and moral dilemmas be? Genetic manipulation might even become a question of fashion and cosmetics. People giving themselves tails or wings for nothing more than the fun of it. It could be completely down to what they choose. And once humans start spreading out across the stars, adaptations would cause them to become more and more diverse culturally and even genetically. Our human race may split off into separate species altogether. So, what do you think? Would this be a future you recoil from, or is it one that excites you? I'd love to see your discussions in the comments. There was a time when visiting Mars was a thing purely of science fiction, relegated to the likes of John Carter or Arnold Schwarzenegger's character Douglas Quaid from Total Recall. However, thanks to recent advances in technology, the first humans might be walking on Mars within this decade. They'll be brought there by Starship, a rocket in development by SpaceX, which hopes to get humans to Mars by as soon as 2030. Once a colony is established, many others will start making the 6-month trip to the Red Planet. Perhaps this is a thing that you might do in your lifetime. Even if made as a commercial vacation, the journey to Mars is no trivial cruise or long-distance flight. If you go, you will not come back the same again. You quite literally could be changed forever. I'm Alex McColgan, and you're watching Astrum. Today, we will be taking a look at Starship and imagining for ourselves what a voyage to the Red Planet might be like. SpaceX company founder Elon Musk has long aspired to take humans to Mars. In 2005, Musk first declared to the world his plans to create a long-term, high-capacity rocket, one capable of carrying massive weights into orbit. However, it took over a decade of development and tinkering with the idea for Starship to be first officially announced. Starship is a super heavy lift launch vehicle made to deliver 100 metric tons to low Earth orbit and beyond. It is fully reusable, able to launch and then land itself thanks to high levels of control from its multiple engines as well as its flaps, which extend to slow its fall in atmosphere. Starship is a spacecraft of 2 parts. The first part, the Super Heavy booster, is a 69-meter tall behemoth filled primarily with 2 massive tanks of liquid oxygen and liquid methane fuel. It sports up to 33 Raptor engines, capable of producing between them around 76 million newtons of force. The Starship spacecraft, which is the second stage, sits on top of its Super Heavy booster. It's 50 meters long, with a diameter of 9 meters, and is equipped with a distinctive shiny exterior. This shine is important. Starship is not made from the usual carbon fiber, which is a material you might expect in a rocket, but instead a version of stainless steel, a similar material to what you might find in your knife and fork. Stainless steel is a surprisingly useful building material for rockets, it turns out. It can heat up to temperatures of over 1,300 degrees Celsius without melting or warping, which is useful when you intend your rocket to perform atmospheric re-entry. But more than that, it is cheap and easy to mass produce. This speaks to Musk's vision,
he intends to produce entire fleets of these. In his mind, Mars is somewhere that humans will set up a serious presence, and when that happens, it's only natural that materials, products, and personnel will need to make the journey to and from the Red Planet. Which brings us to Starship's payload. As previously mentioned, this mostly hollow space is able to carry around 100 tons. It has a 9-meter diameter circular base and is 18 meters high, tapered to a point, allegedly because Musk thought it would be funnier to have a pointier rocket. It can be used to carry satellites, which can then be released into orbit for commercial ventures. However, SpaceX has made it clear that when it comes to the trip to Mars, they intend to put humans in this area. Currently, SpaceX has not revealed what the interior design of this habitation will definitively look like, but there are some preliminary ideas. So, let's explore those ideas. Let's imagine that in a couple of decades from now, we receive a call that tells us colonists are needed on Mars and it's time to make the long trip. To begin with, you would travel to a SpaceX launch site, possibly in cooperation with NASA, and would meet up with your roughly 100 co-passengers. 100 passengers are how many SpaceX thinks it can comfortably fit inside of Starship, although Musk mentioned that this number could be as high as 200 if passengers were willing to really cram themselves in there. You might do well to get to know some of these people now, as unlike with a regular trip in an aeroplane, you are going to be spending a lot of time with these individuals. On an airplane, it is often tempting to watch a film, read a book, or go to sleep. However, you can't only do that for 6 whole months. These are the people you are going to be eating breakfast with. You will spend your free time together. You may form friendships. Human interaction is important for healthy psychology, and there is no way off this flight midway if you find there's someone you don't get along with. Better start off by making friends early. Together, you will then be ushered into the rocket itself. Likely for the initial launch, you and the others will need to strap into your seats. All that thrust beneath you will crush you with powerful G-forces that will push you into your chair. More intense than the most powerful roller coaster, a certain level of physical fitness will be an important element of this part. If there is a medical emergency on the flight, you are not going to get proper hospital treatment until you get to the other side. You will likely have been screened before traveling. Launch and liftoff will only last about 9 minutes. At some point in this journey, the super heavy booster will detach and drop back to Earth. The booster is reusable, and by controlling its descent, it will land perfectly on a landing pad, ready to be filled up with fuel again for another voyage. Thrust will switch over to Starship. While in the atmosphere, it will use 3 of its Raptor engines, but will switch over to the other 3 once the ship has reached true space. These secondary Raptor engines have larger nozzles, which are better suited to propelling the ship through space. All of this will be enough to get you up past the Kármán line and into space. You will now be traveling at thousands of kilometers per hour. However, as the boosters cut off and as gravity drops away, you will suddenly experience weightlessness. Gravity, as we discussed in this video, is only a form of acceleration. If we do not accelerate, even if we are traveling at thousands of miles an hour, we will float around. This will be a major feature of the next 6 months of your life. By now, the seatbelt lights will come off and you can begin to explore your environment. Current plans expect Starship to be split up into multiple floors or areas. At the bottom will be crew cabins. You will likely share a cabin with 1 to 2 other people, and conditions will be a little cramped. Above that, there will be a common area for gathering and social interaction. You will see exercise areas and equipment, an important part of space travel. On the International Space Station, where astronauts also spend 6-month stints, exercise takes up 2 hours of their daily routine. You will need to do this too to prevent the loss of muscle mass and bone density. Without it, you will lose considerable weight and may not be able to stand up once you reach Earth's gravity again. There may also be some emergency shelters. Hopefully you will not spend too much time in these, but it'll be important to acquaint yourself with where they are in the event of an unexpected solar flare. One of the greatest threats of space travel is radiation. Prolonged exposure can result in cancers and other negative health effects. Solar flares represent a hazardous spike in this radiation level, and the captain might at times require you to take refuge in these thick-walled shelters for the good of your health. Mealtime will be a little different from what you are used to. The food you will eat in space must be able to survive for months on end without going bad. There is no opportunity to restock. The International Space Station does not even have a fridge. All of this means that vacuum-sealed, rehydratable food will be the order of the day. Whatever you eat, be wary of mess. You will not be able to sprinkle salt or pepper on your food, as the low gravity will send this flying into the air. Thus, these will be provided in liquid form. As for water, well, the only way to carry enough water for 100 people to Mars is to have excellent recycling systems. So, anything that comes out of you will likely be siphoned off and recycled, only to be served back to you at your next mealtime. It's best not to think about it. Then again, this is not that different from what happens on Earth. All the water you drink has been through many other living things systems multiple times. As I said, best not to think about it. Showers will not likely be present, as without gravity, water does not flow. Astronauts tend to use waterless shampoos and rub themselves with wet flannels. Toilets will be something you need to strap yourself down to use, and they will be vacuum powered to get rid of waste and to stop it floating around. Sleep will take a little adjusting too, as there will be no true night and day anymore, and gravity will not pull you down onto a bed. Think you could get used to all of this? Well, here is where the really strange things start happening. As you travel through space, you will start to experience changes. Under the effects of low gravity, you will start to grow taller. Some astronauts gained an entire inch of height after 6 months in space. Your face will become redder and puffier as your heart, so used to fighting against gravity to pump up blood through your system, will find itself too good at its job in a weightless environment. This change can lead to health issues, thickening of carotid arteries, and sight issues. These are not all fully understood by scientists, as there are not many examples of humans in space to test from. But perhaps the strangest of all, your very DNA will change. There is always some adaptability in human DNA. Certain genes are turned on or off at certain times in our life under certain conditions. In a twins study performed by NASA in 2019, 2 twins with identical genetic material were tested. One was sent up to space for 6 months, the other remained on Earth. When the 2 reunited and were tested again, it was found that the astronaut twins' DNA had changed in how it was expressing itself, creating differences between him and his brother. There were shortened telomeres, weakening of the immune system, and issues with bone formation. It's worth noting, upon arriving back on Earth, most of these changes in genetic expression reverted back to normal after 6 months. However, 9% of them did not. In ways we do not fully understand yet, spending time in space changes you, most likely because of the radiation the astronaut experienced. So, eventually you will arrive at Mars. Starship will fall at an angle and will use its flaps to shed an incredible 99% of its kinetic energy aerodynamically, traveling in a long arc through the atmosphere before eventually bringing you to the planet's surface. You will step out into the biodomes and sniff the manufactured Martian air. Starship will be checked over and then refueled using oxygen and methane extracted from Mars itself. As for you, you will have plenty of time to ponder. All journeys change us, but yours may be the one that you can never change back from. The you that left Earth will never truly return home. But then, perhaps that's just how it always is. Right now, the Perseverance rover is located inside the Jezero crater on Mars, roughly 363 million kilometers away from us. And yet, despite this distance, Perseverance is sending us thousands of images, videos, and scientific data from its various sensors and instruments. If you think that's far away, the Voyager spacecraft took and sent the famous pale blue dot image from 6 billion kilometers from Earth. That's 40 times the distance between Earth and the Sun. We currently use radio waves to transmit data to and from spacecraft. That's right, the same kind of waves used to listen to the radio. However, at interplanetary distances, Even with the incredible and expensive technology in use today, data transfer speeds can be far slower than dial-up internet. This severely limits how much data a probe can capture, as well as the speed in which it's received, which is why NASA has something new up its sleeve. I'm Alex McColgan and you're watching Astrum. Join with me today as we understand how NASA stays in contact with spacecraft billions of kilometers away and explore the new kinds of technology NASA have just launched in the field of deep space communication. Unsurprisingly, the probes and rovers of NASA missions do not have extremely powerful radio antennas themselves. They simply aren't big enough or powerful enough to house them. They have small but directional and efficient antennas which transmit their data. This means most of the heavy lifting needs to come from huge radio antennas on the Earth itself. NASA uses something called the Deep Space Network to communicate with its spacecraft. The Deep Space Network is the largest and most sensitive scientific communication system in the world. The Deep Space Network received and relayed to the world the first TV images of astronaut Neil Armstrong setting foot on the surface of the moon in 1969. It was called on to support the nerve-wracking Apollo 13 mission after the rupture of an oxygen tank, which forced NASA to abort the planned lunar landing. During the critical re-entry of the capsule, it was essential that engineers on the ground maintain contact with the astronauts on board. The spacecraft's minimal power was needed for re-entry, with little left over for communications. The Deep Space Network was able to capture these whispers from space, and it helped bring the astronauts home. And of course, the Deep Space Network maintains contact with every ongoing deep space NASA mission. It can even talk to the rovers on Mars. In fact, each antenna can receive multiple incoming signals at the same time. However, it only has the capability to transmit one at a time. So, how does it work? Well, it's a network of 3 facilities containing multiple giant radio telescopes, with facilities located in California, Spain, and Australia. Each facility has multiple antennas, and while the size of the antennas is important, it isn't the only factor to consider. Their placement is actually very important too. They are all equidistant from each other and are approximately 120 degrees apart in longitude, with each facility situated in semi-mountainous, bowl-shaped terrain to help shield against radio frequency interference. The location of the 3 sites means that at any given moment in the Earth's rotation, almost every area of the sky is covered by an antenna, so there aren't many communication blackouts with ongoing missions. The Deep Space Network helps gather the science data acquired by the spacecraft. It transmits commands and uploads software modifications to spacecraft. While the Deep Space Network tracks, sends commands to, and receives data from all NASA spacecraft beyond the moon, the network also supports other international space agencies like the European Space Agency, Japanese Space Agency, and the Indian Space Agency. However, there are downsides to the system too. They require large antennas on Earth, ultra-sensitive receivers, and powerful transmitters in order to maintain contact over the vast distances involved. And as incredible and as versatile as the Deep Space Network is, it is showing its age. It's been the only communication system for NASA for decades. Replacing major components can cause problems, as it can leave an antenna out of service for months at a time. Plus, the older 70-meter antennas are reaching the end of their lives. At some point, these will need to be replaced. And in reality, they are not very efficient when it comes to interplanetary missions. As I mentioned, at tremendous distances, the data transfer rate is painfully slow. It took New Horizons over 2 years to send back all the data it collected from just the one Pluto flyby. So, what can be done better? Well, this is where the Laser Communications Relay Demonstration mission comes into play. Since the dawn of space exploration, NASA has used radio frequency systems to communicate with astronauts and spacecraft, but the LCRD will demonstrate the capabilities of optical communications. Launched on the 7th of December 2021, this space relay is a new, better, faster, and more advanced way of transmitting data in space, using infrared laser communications rather than radio waves. Infrared light has higher frequencies when compared to radio waves, and that means more data can be packed into each transmission. This antenna in space can send data to Earth from geosynchronous orbit at 1.2 gigabits per second. With it, it's almost like NASA is upgrading from ADSL to fiber internet. Including the benefits of the increased data transfer speeds, the LCRD will also help NASA remove the need for missions to have direct line of sight to antennas on Earth. And its geostationary orbit will mean it's always in view of the ground stations on Earth. A geostationary orbit means the spacecraft is orbiting Earth the same speed as Earth's rotation, meaning the same side of Earth is always in its view. Now, this is a technology demonstration mission, but it is hoped that the LCRD will prove the capabilities of optical communication in space. Using this system, we should have a bandwidth increase of 10 to 100 times more than radio frequency systems. Additionally, optical communication instruments are smaller in size, and they weigh less than radio instruments. So, for a spacecraft using optical communications, that would mean there would be more room for science instruments, or simply a less expensive launch due to its lower weight. In fact, the entire LCRD payload itself is only the size of a standard king-size mattress, compared to the 70-meter behemoth radio antennas the Deep Space Network currently utilize. Helpfully, optical communication systems are also very power efficient. But the major downside of using optical signals is that they cannot easily penetrate cloud coverage, so NASA must still build a system flexible enough to avoid interruptions due to weather on Earth. The LCRD will test this by transmitting data to 2 ground stations, one of which is located in California, with the other in Hawaii. These locations were chosen for their minimal cloud coverage. So, what will the LCRD actually be used for? As part of the technology demonstration, it will be able to relay data from the ISS to Earth at much greater speeds than currently possible. Because the ISS is orbiting so close to Earth, it's only ever in view of ground stations for very short periods of time. However, if it is relaying data to the LCRD, which is high above the Earth, it will remain in view of the LCRD for half of its orbit, and so can relay data to it for much longer periods of time. And assuming LCRD is proven a success, we do have some upcoming missions that will utilize this new optical capability. The Orion Artemis II mission, which is planned to launch in 2024, is set to transfer ultra-high-definition video over infrared light to Earth, which will show Artemis II astronauts exploring the moon in a definition we've never seen before. In addition, the Psyche mission, which is planned to be launched in 2026, will go to an asteroid over 240 million kilometers away from Earth. Psyche will carry the deep space optical communication payload to test laser communications at this distance. These missions will help pave a way for laser communication in the space field. The increase in bandwidth will fix one of the major bottlenecks of science collection that has really hindered missions in the past. Being able to transmit ultra-high definition video from planets and asteroids going forward seems like an incredibly exciting prospect, and honestly, I just can't wait. Plus, should we explore the far reaches of the solar system again, hopefully this time we won't have to wait years at a time for all the data to reach us. So there we have it, almost everything you could want to know about deep space communication systems and how future missions may enjoy a bandwidth we've never experienced before. I hope I earned your like and subscription today. Thanks for watching. I really want to give a huge thank you to our astronauts on Patreon. It's really becoming a thriving community, and I've loved reading all your messages and comments over there. If you'd like to join in, then you can visit the link in the description to become an astronaut and bring the channel more stability than the algorithm. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.